Okay, so you sent us down a really interesting path this time, dental ceramics.
Yeah.
Now, I have to admit, when I first heard that, I kind of pictured, fine china teacups, delicate stuff.
Right. Yeah, that's a common thought.
But turns out, in dentistry, these are serious materials, aren't they? So our mission today, basically, is to get past the jargon, break down what they are, why some are super strong, others look incredibly real, and how they help our Royals. We've got a video lecture, a pretty detailed PDF too, so let's dive in.
Absolutely. Think of this as getting the essentials without wading through all the dense material science yourself. We'll hit on what they're made of, their key properties like how they stand up to chewing, how good they look, how well our bodies accept them.
Right.
We'll also touch on, their drawbacks, where they really excel in treatments, how dentists sort of categorize them, and the difference between ones with a metal core versus the all-ceramic kind. It's a lot, but we'll unpack it.
Okay, sounds good. So let's start right at the beginning.
Yeah.
What exactly are dental ceramics? It's got to be more than just like tooth-colored plastic, right?
Right. Oh, yeah. Definitely more complex. Fundamentally, they're inorganic, non-metallic materials. So think building blocks made from metallic or semi-metallic elements, but combined with things like oxygen, phosphorus, sulfur, basically non-carbon stuff.
Inorganic, non-metallic. Got it.
And that basic chemistry puts them in a whole different category from, say, the metal alloys or the plasticky polymers also used in dentistry.
That seems important. So they're their own thing. How does that difference affect how they actually work in your mouth?
Well, a really key difference is bonding. The atoms in ceramics have these strong kind of directional links. Imagine really tightly connected Legos.
Yeah.
That gives them great rigidity, great for resisting chewing forces.
Okay, rigidity, strong.
But, and this is the trade-off, unlike metal that might bend or deform under pressure, ceramics are more likely to just fracture if you push them too hard. They're brittle.
Ah, okay. So strong but brittle, like glass.
Sort of, yeah. But on the plus side, a huge plus is how they handle light. They can mimic the look, the translucency, even the feel of natural teeth way better than metals or polymers usually can.
So strength comes with brittleness, but you get amazing aesthetics. Okay.
Yeah.
Now, the video mentioned a few main types. Can you give us the quick rundown?
Sure. The big categories are silicate glasses, porcelains, glass ceramics, and then the highly crystalline solids. It helps to think of it like a spectrum, almost.
Like spectrum. How so?
Well, at one end, you have silicate glasses. They're the champs for looks, very translucent, but generally the weakest. Then as you move along towards porcelains, glass ceramics, and finally the highly crystalline ones like zirconia,
Zirconia. Okay. Heard of that one.
you gain a lot more strength, serious strength, but you might lose some of that natural see-through quality. It's all about how their internal structure balances those things.
Interesting. So let's peek inside those structures. Silicate glasses first. What makes them tick?
Okay, so silicate glasses, they're primarily based on silicon dioxide. Silica, same basic stuff as window glass or sand.
Right.
In dentistry, they're loved for that light transmission, that realistic look. Structurally, it's a network of silicon and oxygen, maybe some potassium or other bits mixed in. But that network can have gaps, little imperfections at the atomic level.
And those gaps are the weak points.
Essentially, yeah. That's what makes them the least strong of the bunch. Beautiful, but handled with care, relatively speaking.
Got it. The supermodels look great. Don't ask them to lift heavy things. Okay, what about porcelains? How do they get tougher?
Porcelains are kind of like beefed up silicate glasses. They mix feldspar, silica, alumina, other metal oxides, and then heat them up so they fuse together. That's called sintering.
Sintering. Okay.
The key ingredient there is often alumina. It acts like a reinforcement within the glassy structure, making it stronger, more durable than just plain silicate glass. You mentioned older crowns sometimes had porcelain over metal.
Yeah, my grandpa had one, I think.
Right, that porcelain layer benefited from that added strength.
Okay, so adding alumina is like putting rebar in concrete, maybe? Makes it tougher. Next up, glass ceramics. The name sounds like a hybrid.
Exactly what they are. They start out as glass, but then they go through a special heat treatment that makes tiny thermic crystals grow within the glass.
Oh, cool. So you get both.
You get kind of the best of both worlds, yeah. The remaining glassy part still gives you pretty good aesthetics, while those embedded crystals seriously boost the strength and toughness compared to regular glass or porcelain. They might not be quite as translucent as pure silicate glass, but they look very natural and are much more robust.
And a multi-tool then.
Good all-rounder.
Yeah.
Okay, now for the heavyweights. Highly crystalline solid. You mentioned alumina and zirconia. That's where the serious strength lies.
That's exactly right. Highly crystalline solids, alumina, zirconia, these are the powerlifters. Crystalline just means their atoms are arranged in a really neat, orderly, tightly packed structure, like stacking bricks perfectly with zero wasted space.
Very dense, incredibly dense, especially zirconia. There's hardly any space between the particles, and that's what gives them phenomenal strength and resistance to cracking. But because they're so dense, light doesn't pass through as easily, so they tend to be more opaque, less translucent.
Okay, less see-through. Now, you said something earlier that stuck with me, zirconia being comparable in strength to steel. That sounds kind of nuts for something in your mouth.
It is pretty amazing, isn't it? Its flexural strength, basically how much it can bend before it breaks,
Yeah.
is genuinely in the same league as some steels. That's why you sometimes hear dentists call it white metal.
White metal, huh?
Yeah, it gives you that incredible durability, but in a tooth color. So for someone who grinds their teeth, a Bruxer zirconia can be a fantastic, really long-lasting option.
Wow. Okay, from delicate glass to steel-like toughness, all under the ceramic umbrella. That's a huge range. Beyond these specific types, are there any, common threads, properties they all share?
Yes, definitely. Generally speaking, dental ceramics are very chemically stable. They don't corrode easily. They don't react much with saliva, food, drinks, mild acids, that sort of thing.
That's good. You don't want stuff dissolving in your mouth.
Exactly. Mechanically, as we've seen, strength ranges from good to excellent, and they resist fracture pretty well up to their limit. Thermally, they handle processing heat, but they are brittle and susceptible to thermal shock. Sudden, big temperature swings aren't their friend.
Like pouring cold water on hot glass?
Kind of, yeah. A rapid change can potentially cause a crack. Very importantly, they're highly biocompatible. Our bodies generally tolerate them extremely well, no allergic reactions usually. And of course, the aesthetics, their ability to match natural tooth color and translucency, is a massive advantage.
Lots of positives. But the sources mentioned downsides too. What are the main limitations we need to keep in mind?
The big one, as we touched on, is that brittleness. Even the strong ones. They don't really warn you by bending first. If the stress gets too high, they can just fail suddenly.
Like dropping a ceramic plate versus a metal one.
Good analogy. The other main factor is often cost. Manufacturing these materials requires high-purity ingredients, specialized furnaces, often complex processing or CAD/CAM technology, skilled technicians. It all adds up, making them generally more expensive than, say, a metal filling or even some polymer composites.
Brittleness and cost. Got it. Okay, let's shift to where we actually see these being used. What are the common dental applications?
Oh, they're super versatile. A very common one, especially historically, is the metal ceramic crown, sometimes called a PFM, porcelain fused to metal.
Right, the one with the metal inside.
Exactly. You have a strong metal substructure, like a thimble over the tooth, and then porcelain is baked onto the outside for the looks, often used on back teeth where you need strength. An interesting point is they sometimes require a bit less tooth trimming than an all-ceramic crown might. Aesthetics are usually good,
But you might see the metal edge at the gum line sometimes.
yeah, sometimes you can get a dark line there. And the overall translucency isn't quite as natural as a fully ceramic crown because of that metal blocking the light.
Okay, so metal for strength, ceramic for looks, a practical combo. What about crowns made entirely of ceramic?
All ceramic crowns, no metal involved. Their big advantage is superior aesthetics because there's no metal interfering with the light. They can look incredibly lifelike, so they're often the first choice for front teeth.
Makes sense.
The flip side is, to get enough strength and good aesthetics just from the ceramic itself, the dentist might need to remove a little more tooth structure to make room for a sufficient thickness of the material.
Ah, okay. Need a bit more bulk without the metal reinforcement. What other jobs do ceramics do?
Well, there are veneers, those super thin ceramic shells bonded right onto the front of teeth. Great for fixing discoloration, small chips, maybe minor alignment issues.
Like little ceramic fingernails for your teeth?
Kind of, yeah. Then you have inlays and onlays. These are like partial crowns, custom-made ceramic fillings used for moderate decay. Inlays fit within the cusps, the bumps on your tooth,
Okay.
while onlays are bigger, covering one or more cusps, sometimes called overlays. And even in orthodontics braces, you can get ceramic brackets that are tooth-colored or clear, much less noticeable than metal ones. The video mentioned a brand, Ice, popular with teens for that reason.
Oh, yeah, clear braces.
And finally, after a root canal, if the tooth needs more support, ceramics can be used for endodontic posts and cores to rebuild the structure inside.
Wow, They really get around in dentistry. Okay, the sources also went into classifying ceramics. Seemed like there were a couple of ways to slice it.
Yeah, two main ways dentists think about them. One is by their internal structure, what kind of crystals are in there, and what's the surrounding glassy stuff, the matrix, like, remember the fruitcake analogy?
Huh? Yeah, the crystals are the fruit and nuts, the glass is the cake.
Pretty much. So based on that, you get types like feldspathic porcelain that's got lucite crystals in glass, great for veneers, metal ceramic layers, looks fantastic, but it's the weakest, remember?
Right, it's a supermodel.
Then aluminous porcelain, more aluminum crystals for strength, good for cores inside crowns, but more opaque. Lucite glass ceramic, also lucite crystals, stronger than feldspathic, good for single front crowns, veneers.
Getting stronger.
Then lithium disilicate glass ceramic. Those lithium and silicate crystals give a really nice balance of strength and aesthetics. Super popular, dentists love it. Brand name like E. Max. Good for crowns, even short bridges.
E. Max, okay, heard that one too.
And then you have the highly crystalline ones as categories themselves. Alumina strong, used for cores but opaque. And zirconia specifically, YTZP, is the dental type that's the white metal. Super strong, great for crowns, bridges, even back teeth, but also pretty opaque.
Okay, that fruitcake breakdown makes sense. What's the other classification method?
The other way is by their firing temperature, the heat needed during processing. This affects the final properties, density, strength, even color.
Ah, like baking temperatures.
Exactly. You got high fusing over 1300 Celsius. That's for the really tough stuff, zirconia, alumina cores, maybe some denture teeth. Medium fusing, 1100 to 1300 C, also denture teeth. And something called pre-sintered zirconia.
Pre-sintered, like partly baked.
Sort of an intermediate stage, yeah. Then low fusing, 850 to 1100 C, very common for the outer porcelain layers on crowns and bridges. And finally, ultra-low fusing, below 850 C, also used for those outer aesthetic layers. Knowing these helps match the right ceramic to the job and make sure it bonds correctly.
Okay, so lower temps for the pretty outer bits, higher temps for the strong inner structures. Makes sense. Now, connecting this back, the sources gave examples of when you'd use which type. Can we recap a few key ones? Like, don't use X for Y.
Absolutely. So feldspathic porcelain, great for veneers, maybe the outside of a front metal ceramic crown, but definitely not for a molar crown on its own or a bridge, just not strong enough. Aluminous porcelain, maybe a single front crown, but still generally avoid molars or bridges. Lucite, glass ceramic, same idea. Single front crowns, veneers, areas without heavy biting forces.
Okay.
Lithium disilicate, E. Max. Now you're getting more versatile. Front and premolar crowns, even short bridges up to the premolars. Good strength, great looks, but probably still not for a long bridge spanning multiple back teeth.
So it has its limits.
It does. For those really high-stress posterior jobs, long bridges, you're looking more at alumina-based cores, maybe glass-infiltrated aluminized zirconia, that you trade off some translucency.
And then zirconia?
Zirconia, YTZP, is your powerhouse. Posterior crowns, long bridges, implant parts, max strength is the priority, even if it's the most opaque option.
Super clear. Okay, let's dig into those metal ceramic systems again. They've been around ages, still used a lot. What's the secret to their success?
Yeah, they have a really solid track record, like 50-plus years.
Yeah.
Good survival rates. We mentioned they're great for back teeth, maybe less tooth removal needed sometimes. And you can even have a durable metal chewing surface if needed. The system basically relies on that metal substructure for strength and the porcelain layer bonded over it for aesthetics.
And the metal itself, it's not just any metal, right?
No, definitely not. It's a special dental alloy. Critically, it has a higher melting point than the porcelain's firing temperature, so it doesn't warp or melt when the porcelain is baked on.
That would be bad.
Very bad. And they contain small amounts of base metals, iron, indium, tin, things like that. These are crucial because when the metal is heated up, before the porcelain goes on a step called degassing or oxidation, these base metals form a very thin oxide layer on the surface.
Ah, the oxide layer. That's the key for bonding.
That's the absolute key. That oxide layer is what the porcelain chemically bonds to. It's mostly an ionic bond, a real chemical connection. Think of it like microscopic Velcro, but chemical Velcro.
Chemical Velcro. I like that. Okay. You also mentioned ultra-low fusing ceramics with these. What's their deal?
Right. Ultra-low fusing porcelains. They sinter, or fuse, below 850 Celsius. The main advantage is that lower heat is even gentler on the metal framework, less risk of distortion. They often have different compositions, maybe more glassy components. Another nice thing is they often polish up really smoothly, which is kinder to the teeth chewing against them.
Lower temp, smoother finish. Good benefits. The video also talked about glass modifiers. What are those doing in the mix?
Glass modifiers are basically additives, usually ions like sodium, potassium, calcium. They get in there and disrupt the main silicon-oxygen network of the glass.
Disrupt it. Is that good?
It is. In controlled amounts, it does several useful things.
Hmm.
Lowers the firing temperature, which we just discussed. It can help control how much this ceramic expands or contracts with heat. It can actually increase strength and toughness, improve resistance to thermal shock, and it affects how gooey the ceramic is when melted, making it easier to shape and glaze.
Wow, they do a lot.
They do, but it's a balance. Too much modifier can weaken the chemical durability over time, make it less resistant to wear or staining. So, gotta get the recipe right.
The secret sauce again. Okay, how do they actually make these things? Applying the ceramic to the metal.
It's a careful process. First is condensation. The technician applies the porcelain powder, usually mixed with the liquid, onto the metal coping, layer by layer. They pack it really tightly to get rid of air and minimize shrinkage later. Good condensation is vital for strength.
Packing it down tight.
Then comes sintering, the firing. It fuses the powder particles. This is often done under vacuum firing. Sucking the air out helps reduce porosity, makes the final ceramic denser and stronger.
Makes sense.
The vacuum is usually released near the end of the firing cycle, and then it finishes cooling under normal pressure.
Yeah.
And that cooling needs to be controlled, not too fast, to avoid thermal stress and cracking.
Vacuum firing, clever trick. Now, getting that bond, the porcelain sticking to the metal, you mentioned the chemical bond. Are there other things helping it stick?
Yes, it's usually a combination of three things. First, mechanical interlocking. They often sandblast the metal surface to make it slightly rough. Tiny irregularities for the porcelain to flow into and grip.
Like tiny little keyholes.
Kind of. Second is that crucial chemical bond via the oxide layer. We talked about the ionic interaction. Really important. Needs a clean metal surface and proper oxidation.
Right, the chemical Velcro.
And third, there's a neat trick with residual compressive stress. Ideally, the metal alloy is chosen so it shrinks just slightly more than the porcelain as it cools down after firing.
Why would you want that?
Because it puts the porcelain layer into compression. It's being squeezed slightly by the metal contracting around it. And ceramics are much, much stronger under compression than they are under tension or being pulled apart. So this built-in squeeze actually helps make the porcelain tougher and resist cracking.
Wow, that's clever engineering. Physical grip, chemical bond, and engineered stress. No wonder they can last. Okay, what about the final touches, glazes, and stains? They make it look real, right?
Exactly. Glazes and stains are all about the final aesthetics and surface quality for both metal ceramic and all ceramic. Autoglaze means during the final firing, the surface layer of the ceramic itself melts just enough to flow and become smooth and glassy. This seals tiny surface flaws, which actually increases strength too.
Oh, so glazing makes it stronger.
It can, yeah, by sealing those micro cracks. Overglaze is applying an extra layer of a special low-fusing glass and firing it again. Gives a nice sheen, but sometimes might be slightly less durable chemically than an autoglaze.
Okay.
And stains are just tinted glazes. Used to add character, mimic natural color variations, little lines, shading near the gum line, can be applied internally between layers or externally. So yeah, glazing and staining isn't just cosmetic, it boosts strength and creates a smoother surface, which reduces wear on the opposing teeth.
Functional beauty. Cool. Now, things can still go wrong sometimes. What are the typical ways these metal ceramic restorations might fail?
Yeah, failures happen. The video mentioned a few modes. Adhesive failure is when the bond breaks between materials. So porcelain lifts off the metal or off the oxide layer.
The bond fails.
Right. Cohesive failure is when the fracture happens within one material. So the porcelain itself cracks or chips, but it's still stuck to the metal. This might happen if the porcelain wasn't condensed well or sintered properly.
The material itself breaks.
Exactly. And then there's just static fracture, a crack developing due to stress over time. The good news is repairs are often possible. Small chips might just be polished smooth. Bigger breaks might involve roughening the area with air abrasion, applying special bonding agents like silane, and then using composite filling material to patch it up. Depends on the break.
Good to know there are fixes. Okay, let's switch gears fully now to all ceramic systems. We touched on them, but let's really get into why they're so popular and the different types.
Right, all ceramics. Big draw is definitely aesthetics and biocompatibility. They can look incredibly natural because light passes through them more like a real tooth. And we use them for pretty much everything. Crowns, veneers, inlays, onlays, even bridges now.
So the types, again, maybe a bit more detail.
Sure. Feldspathic porcelain, still the king for Pure translucency, best for veneers, maybe single front crowns where biting force is low. Lucite reinforced glass ceramics like IPS Empress, step up in strength, good for single crowns, front or back. Veneers, inlays and lays.
Okay.
Lithium disilicate glass ceramics, IPS Emax Presscad, the real workhorse. Great combo of high strength, toughness, and great aesthetics. Handles crowns front and back, short bridges up to premolars, veneers, the lot. Very
A
popular.
versatile one.
Then alumina-based like Procera Alceram, very strong and tough, but more opaque. So good for cores or crowns where strength is paramount, maybe less ideal aesthetically for front teeth veneers.
Strength over beauty sometimes.
Sometimes, yeah. Zirconia-based, lava, zircon, Berkshire, the strongest of the all ceramics, extremely tough, also opaque, so often used for frameworks that get layered with prettier porcelain, or for posterior crowns bridges where you need maximum durability, especially for grinders. The white metal again.
Right.
And there were those glass-infiltrated ceramics in ceram types, another high-strength option, moderate translucency, used for crowns and shorter bridges. So lots of choices depending on the specific need.
Definitely a wide range. How are these actually made? Is it different from baking porcelain onto metal?
Yeah, different techniques here. Sintering powder is still used for feldspathic porcelain, some others. Hot pressing is big for lithium disilicate and lucite types. They heat a pre-made ingot of ceramic until it's soft and press it into a custom mold. Very precise.
Pressing it into shape.
Slip casting is used for the glass-infiltrated ones. You make a ceramic slurry, pour it into a porous mold that sucks out the water, then sinter and infiltrate with glass. And then there's a huge one, CAD/CAM milling.
Computer-aided design and manufacturing.
Exactly. Take a digital scan of the tooth, design the crown or inlay on a computer, and a milling machine carves it precisely out of a solid block of ceramic, lithium, disilicate, zirconia, feldspathic, whatever. Huge technological advance.
Wow, technology making teeth. Now, like with anything, there must be downsides or things to watch out for with all ceramics.
For sure. As we mentioned, they often need a bit more tooth reduction to ensure enough material thickness for strength and looks. Maybe not always, but often.
Okay.
Bonding is absolutely critical. You're relying entirely on that bond to the tooth for retention and added strength. So dentists use special resin cements and very careful bonding procedures. It's not like cementing a metal crown.
More technique sensitive.
Highly technique sensitive, yes. Both for the dentist doing the prep and bonding and the lab tech making it. Cost can also be higher due to the materials and tech involved.
So more tooth removal sometimes, bonding is crucial, potentially a higher cost, and needs skilled hands.
Got it. How do they perform overall then in the mouth? Performance-wise, aesthetics generally superior, especially things like lithium disilicate and feldspathic. Strength and fracture resistance, zirconia is top dog, lithium disilicate is a great balance. Biocompatibility, excellent, very tissue friendly.
And wear? Do they wear down opposing teeth?
That's a good point. They are very wear resistant themselves. If they are properly polished and smooth, they're actually very kind to opposing natural teeth. But an unpolished or rough ceramic surface can be abrasive, so that final polish is really important.
Smoothness is key. Okay, this has been incredibly informative. We've gone from basic chemistry to clinical use, metal versus all ceramic. If you had to boil it down, what's the main takeaway for listeners?
I'd say the key thing is that dental ceramics are this amazing, diverse toolkit. There's no single best one. The choice always involves balancing the need for strength against the desire for the most natural look possible for that specific situation in the mouth.
And remembering they're fundamentally different, those strong but brittle bonds compared to metals or plastics.
Exactly. And we've seen that whole spectrum, haven't we? From the beautiful but more fragile feldspathic right up to super tough zirconia and all the clever materials, science in between, trying to hit that sweet spot.
Yeah.
Understanding how they're made, how they bond. It really highlights how sophisticated modern dentistry has become.
It really does. So thinking about all that innovation, here's something for our listeners to ponder. With materials science always advancing, what do you think is next? Where might we see the next breakthroughs in dental ceramics, especially in nailing that perfect combo of ultimate strength and completely natural aesthetics? What could that mean for future treatments?
That's a great question to end on. The quest for the perfect material is always ongoing, isn't it? It'll be fascinating to see what comes next.
It will indeed. Well, thank you so much for walking us through all of that. This has been a fantastic deep dive. We hope everyone listening feels they have a much clearer picture of these vital dental materials now.
My pleasure. It's a complex but really important area.
Absolutely. If this got you interested, definitely keep exploring the world of dental materials. Until our next deep dive, keep smiling.